All right, hey, what's up, guys? Slide 9. Hey, we just took care of 7th block in the meantime here. So I'm going to use slide 9 in a second. One thing I didn't realize, well, I checked off the area for this one. It's right here. I hope I'm right about that. I didn't do the perimeter. Perimeter is easier. It's an easier calculation. Perimeter is just the sum of all side length, the lengths of each side of this regular pentagon. Of course, it's the pentagon. We know there's 5. Because it's regular, we know it's equilateral. So we know the lengths are the same. And we followed that. We solved for that earlier. And when we got what QC had to equal, and did I do that in my calculator? I don't know what I did here. Hold on. A was 8.09. H, why did I put H there? It doesn't make any sense. I meant to do QC right here, equals 5.87785. Okay, so that's it here. That means we know each side is 11 point, double that, right? Double that to get to that 11.7 or so. So to get my perimeter, okay, right? Perimeter equals, there's a formula for that, but I don't need it here. Perimeter equals n times by s. Perimeter equals n times by s. It's kind of inappropriate, doesn't it? I don't know. Here, perimeter equals n times s. Number of sides for this particular situation is what? 5. And wait, yeah, that's number of sides. S is side length. Sorry about that. Number of sides and then side length. So number of sides is 5. Side length here was 11.7557. Round to the nearest decimal, and I think we'll be fine for that here. Okay, so I'll do 5 times by 11.7557, and I get 58.8. It's about 58.8. Hooray! All right, that's just in centimeters. Remember, that's a one-dimensional. Each one of these is one dimension, so just we don't have the squaring here. We need the squaring for the area because that's a two-dimensional calculation. Right? Base times height, 2 dimensions. Here, this is technically 1/2 apothem times the perimeter. Anyway, just give you the whole formula. I don't want to do that here. All right, slide 9. Let's do this one. Let's do it faster. I'm assuming you did this with me. I know it's a lot to look at. Let's maybe write a little bit less and focus really on just how to do it real quick here, okay? Let's do this here. I'm giving 10 centimeters. I'm going to read this. I'm going to be like, this is my diagram. They're asking me the same exact thing, okay? My radius is 10 centimeters. This is a hexagon. Remember, we had to use trig. Okay, to find, right, the base and height of each congruent isosceles triangle. Okay, what do we mean by that? Well, boom, we got a radius here. That's 10 centimeters. That's 10 centimeters. What do I do next? Oh, I'm on Desmos now. I'm not on Desmos. I can find my altitude, otherwise known as the apothem of this. We'll explain what an apothem is a bit later. If I drop in an altitude here, boom, okay? Altitude is simply from the vertex perpendicular to one of the sides. Can't quite do it with a straight side, straight here. There we go, that looks better. Okay, perpendicular. I form 2 congruent triangles. Radii, all radii are congruent within a regular polygon because it's their all radii of the circle that's circumscribed about it. Okay, so I know that, and I know that this is congruent to itself. So this is HL right here. Altitude is using the right angle. So those are 2 congruent to one another. I know that the interior angle of, so each interior angle of a regular hexagon, I know it's 120 degrees, okay? Because 6 minus 2 times by 180 divided by 6, well, that's 4 times 180. Anyways, you've done this a whole bunch of times. 4 times 180 is 720, divided by 6 is 120. So I know that this down here is 120 degrees, okay? If these are all forming congruent triangles, I know that that 120, that this actually just bisected. It does, can we prove it? We can prove it that this triangle would have to be congruent to that triangle. These are congruent isosceles triangles. They're actually equilateral for hexagons here, okay? So what can I do? I can make this 60 degrees because I'd have the other 60 degrees out of here. Part plus part equals whole. They equal 120 right here, okay? So I know that's 60 degrees. I know my radius is 10 centimeters. Okay, radius is 10 centimeters here. So what do I need to do? Well, I got a 10, maybe I'll do this on a different, triangle. Okay, I'll do that maybe, yeah, let's do it over here maybe. I didn't like how this is printed, 10 centimeters here. I'll be very specific. This is 10 centimeters. Okay, this is where I'm going to introduce my, it's off here, my altitude. There we go. And 120 gets split 2 ways. this is going to be a 60-degree angle. So all of a sudden, we have right here a right triangle where we know one of the acute angle measurements is 60 degrees. We know what one of the sides is. What's that tool? What's that tool we're going to use? We're going to use trig. Heck yeah, let's do it. Strap yourselves in. I like this stuff. This is good stuff, isn't it? I'm like, no. Leave me alone. It's better than I just give you the formula. It's so lame. I want you guys to work with it here. All right, check it out here. I want to get this. This is technically called the apophthegm. We'll get to that later. But this is the height of this triangle. I want to get the area of that one here. I can get the apophthegm here. And then I can also get 1/2 of the side length, whatever the side length is here. Okay, and this is, it's a 60-degree angle. I can use shortcuts. Check it out here. So I don't even use trig. I use special right triangle shortcuts. I might redraw this down here to make this hopefully a little bit more clear. Or I can do this. If this is 10 centimeters, this is a 60-degree angle. That's a 90-degree angle. This is a 30-degree angle. I have a 30, 60, 90-degree right triangle. So what do I know about the shorter leg of 30, 60, 90-degree right triangle? It's exactly half as long, 5 centimeters. Okay, so this is 5 centimeters here. Well, this has got to be 5 centimeters. Check it out. Wait a second. This is 10 centimeters. This is 10 centimeters. So you know what? The side length is also 10 centimeters, as is the radius. So guys, in a regular hexagon is this special kind of honeycomb-like thing where each regular hexagon is composed of 6 equilateral triangles. These are all the same. Oops, not that, but this. They're all 10 centimeters. So here, that's 5 centimeters, okay? And then what about this? What about the longer leg of the 30, 60, 90-degree triangle? Well, the longer leg is exactly √3 times longer than the shorter leg, than the 5 centimeters thing here. So what am I going to get? I'm going to get 5 √3 centimeters for that altitude right here, okay? Bringing it all back together. Ooh, lots here. I want you to look very closely at this here. Bring it all back together. Maybe I'll do it with this triangle here. What do we know about each of these triangles? We know the height is 5 √3 centimeters. We know that the base is 10 centimeters. So what can we do? Area of one triangle equals 1/2 its base times by height. We're using that formula that you knew in middle school, and you can be easy to forget, but remember, triangle is half of a parallelogram, so 1/2 its base times by height. Okay, 1/2 base times height is 1/2 5 √3 times by 10, right? Because it's a 10 centimeter base here for that freaking triangle right there. Okay, 1/2 times by 10 is 1/2 times by 10 is 5, and 5 times 5 √3 is 25 √3. So there it is. We can get an exact answer for this. The area of this is 25 √3. Can't forget them. Square centimeters, because we are given a unit of measurements that this figure is measured in. Each dimension is represented by centimeters. The area, the dimensions, the two-dimension in between, two-dimensional area in between, but this bounded would be in terms of square centimeters, equivalent to 25 √3 square centimeters. And I think that's, if you get an about answer, right? Maybe you want to check your answer about in your calculator. I'm going to do it. I'm going to hit the square root of 3 is about 1.7, because I've studied this stuff a little bit here. Well, 1.73. I'm going to multiply by 25, so it's about 43. So they said round, so maybe they weren't expecting you to come up with an exact answer. So about 43.3 square centimeters. Boom. All right. Well, that's not your answer. I probably shouldn't have boxed that up because I want to get the area of the whole freaking regular hexagon here. So I got my area of the hexagon. Well, how many equilateral triangles are there? There's 1, there's 2, there's 3, there's 4, there's 5, and there's 6. Here we go. It's so hard to see. I said this would be less messy than the last video, okay? So area of the hexagon equals 6 times by the area of one of the triangles, okay? Area of the one triangle equals 25 √3 over